online lecture. Okay, so today we are going to discuss about the fully developed flow or developing region entrance length, that kind of which relates with the boundary layer formation. So here in the first slide, you can see the heading itself is a brief side comment developing flow. So what is developing flow and what is fully developed flow? That is what we are going to discuss. So from the picture, you can see different profiles, velocity profiles. See, whenever at the entrance region, so what at some place where if I am extending this to a tank, so this is a tank. Let's assume it has a tank. Okay, so water is there. This is the surface of the water. So fluid is there, and so, but this fluids is flowing in this direction, in the positive x direction, and you can see when it enters into the pipe. Hereafter, there is a pipe, and the front view we can see it as a rectangle. So it's a pipe, or it can be a channel, rectangular channel. So this is a pipe. So you can see, okay, mm, surface of the pipe or the walls of the pipe. This red line indicates the walls of the pipe. So here it is coming with a uniform velocity of u infinity. Let's say it is a uniform velocity of u infinity. And once it comes in contact with the solid surface, so these are the surface which fluid comes in contact, and this is the surface of the pipe where fluid comes in contact. So the fluid particles, or let's say one molecule comes in contact with the um, if the solid surface, what will happen? The fluid will take the velocity of that particular surface, because anyway, it's obviously means it obvious that this particular uh, it's well aware that this solid surface it is stationary. That pipe is not moving, so the surface will also will be stationary. So any fluid particle which comes in direct contact with the surface will take that particular velocity, which is of zero, since the surface is not moving. So that condition is called no slip condition. It is called no slip condition. There is no slip. There is slip means it is moving. On the surface, it is something is moving. It's slipping over the surface. We can say no slip means it is not slipping and it is fixed or attached to the surface. So that particular fluid will get zero velocity. But at the center, anyway, it will be that whatever velocity which it is entering. So there is a gradient of what gradient between gradient of gradients, or the difference in velocity at the surface and at the center. So that means, so here it is zero, and slowly this velocity is gradually increasing from that zero to this center region, center velocity. And so how it is developing? So that profile is developing. That is called entrance region. The length to till what length the velocity profile develop, gradually develop changing. You can see this is the cross section where first the cross section, section 1, uniform velocity we can see, because it is at the beginning of the pipe. Next cross section is here. You can see the profile is developing. This is second cross section, and again if you take the third cross section, again this profile, that velocity profile is gradually changing in the both x and both direction. That means if this is one direction y, this is x direction. So velocity profile is changing in with respect to x as well as y in the developing region. Why I am saying x? Because at this cross section, second cross section, one profile, and the third cross section, another profile. So that profile changing, that means u is varying with respect to x. And how we can say with respect to why it is varying. So if we go from this point, from the bottom to top, it is varying. So velocities are of different values. At x equal to 0, sorry, y is equal to 0 at the surface, and y is equal to at that both top and bottom surfaces, it will be 0. But at center, the velocity is maximum. So that is in the vertical direction also, velocity is varying, and in the horizontal direction also, velocity is varying within the entrance region or hydrodynamic entrance region. That is what, see, this length till then it will vary with respect to x and y is called entrance region. Okay, so next, so this cross section also, if you take the fourth cross section, again somewhat the profile is different compared to the third and second. But once it reaches at some point within the tube or pipe or channel, this cross section, this velocity will, profile will develop completely, fully developed velocity profile. You can see this fully developed. Why it is called as fully developed? Because it is no more changes in the x direction. We won't, there won't be any change in the x direction. That is called as fully developed. So if I am taking a cross section, you can see, if I am taking a cross section here, this is the fifth cross section, this is sixth cross section, the same profile I will get it here. What that same profile, if I am copying that profile, I will get the same profile. See, like this, same profile I will get it. So I can draw it like this. So the velocity arrows, center point. So this fifth and sixth, this profile is the fifth profile, and sixth, this is the sixth profile. Both are same. So up after this entrance region till here it is developing. After that it is not developed. That is fully developed. And we or u is a function of is what is a function of y only. U is not a function of, or not a function of what, x. That is the thing you have to keep in mind. U is a function of y only after the developed region, because y in the vertical direction, y changes, u is changing. And you have to explain like this: in the entrance length or developing region or entrance region, the u is a function of x comma y, and once it is developed, you will become a function of y only. This is after developing, fully developed. This is fully developed. Okay, and this is developing. This is developing. This is the thing you have to keep in mind. Okay, how u varies now. So that is the thing. So we have in this particular developed region, we can write. So u is a function of, in developed region, u is a function of y only. That means dou u by dou x. That means gradient of u with respect to x is equal to 0. That you can say in the fully developed region. Current exact solution is for fully developed region. That is dou u by dou x is 0. Now gradient in the x direction. Now velocity gradient in the x direction. That is another expression or mathematical expression of fully developed flow. So next we are going to discuss about exact solutions of Navier-Stokes equation. So far we discussed about Navier-Stokes equation and what is the application of that Navier-Stokes equations, and what is the exact solution. Two exact solutions of Navier-Stokes equations are there. One is Poiseuille flow, another one is Couty flow. As we discussed earlier, in Navier-Stokes equation there is a non-linear term which is nothing but that convective acceleration term. See, if you go back and see, you can see this is the local acceleration term. This is the convective acceleration term. Okay, this is pressure force, viscous force, body force. So this term, this convective acceleration term is non-linear in nature, and because of that, it is very difficult to solve the Navier-Stokes equation. If we, because the exact solution means there won't be any non-linear term. So somehow, because of with some assumptions, the non-linear term will be vanished, and we will get exact solutions. So the two cases are there.